Yo guys, uh, so it's 3 right now. I'm supposed to be sleeping, but I'm not sleeping because I've been constantly thinking about stuff related to work. Yeah, and this has become a problem, like a problem. uh, so usually it's a good thing when like I'm constantly thinking about work, but right now the issue is there's a project which I worked a lot on and I need to switch away from it. So basically, like, cut the thing and just move on to whatever the next thing is, probably sleep, but it's not happening. I'm not able to do that. Like, like I'll sleep, I go to bed and stay there for 5 minutes, and then suddenly a thought pops up, and then I don't know, I get triggered basically, right? I become alert. Uh, I guess this thing even has some sort of technical names, like starts from Z or something, Zig something. But the idea is that people who are very deeply involved in some project or something like that, usually researchers, uh, they sort of have this repeating thoughts, like not repeating thoughts. It's like your brain sort of holds everything that you've been doing in the project, right? So like think about your brain as sort of a computer, and then what's happening is like you have layers of cache, right? Cache, whatever. So the the largest layer, the one with the most memory, it's sort of holding all of this data related to uh, the work that you're doing. So the moment that you try to think about something, it will just try to connect it with whatever you've been thinking of. And that's what's causing this. Like, even if I try to distract myself, so I don't know, I just went on YouTube, did my usual thing that I'll just go through nonsense videos. Nothing works. Nothing works. Like, the most rewarding thing that I can think of, the most pleasurable thing that I can think of at this moment is like is stupid stuff, like, creating an Ethernet transmitter for my FPGA thing. So yeah, yeah, it's just, this is so insane. As in, it's not supposed to be fun. Like, this isn't stuff that's supposed to be fun. It is detrimental to my health, to my life in general, because this isn't a project which I sort of have officially, taken responsibility of, right? And more than that, it's something which is like an emotional detriment to me, because this project is like having some sort of baggage around it. So the sooner I stop working on this, the sooner everything gets better. But then I can't stop working on it if it's in the end a rewarding thing for me. If in the end that's what my heart wants to do, how can I do it? Like, how can I just say that no, let's not do it? I don't know what to do. Like, is this is not something that usually happens. Usually what happens is, if I get like really interested in something, I'll just speed run it. Like, let's say I get interested in some series, I'll just binge watch it over 1 or 2 nights, and then it'll be over. That's it. And then my brain will just free up, and I'll be able to move to whatever is next, right? Maximum I'll want to go back to it just to like rewatch the thing, watch clips of it or something like. But I won't want to sort of actively keep pushing. Same thing with my projects as well. Like, what usually happens is I'm able to just brute force my way through most of my projects. Assignments, I can just brute force through it. The stuff that I was doing on my internship, I literally just brute force through it. I was sleeping in my office, more or less. Like, I get so stuck at the thing that I'm not able to think of anything else. Like, that takes highest priority. And right now what's happening is that I am stuck like on this thing. It's still something sup- that's sort of taking highest priority, but it's not supposed to. I consciously want that it doesn't take highest priority. I actually want to get away from the thing, but I'm not able to. Like, yeah, uh, so why am I making this video? Like, if sleep is my highest sort of immediate important thing to do, why am I making a stupid YouTube video about this? Well, as stupid as it may sound, Gemini suggested me to do this. So the idea is that uh, my brain does not let go of all of this because it fears that if I don't have it like stored somewhere, all this information, then it will basically be deleted. All this nice uh, sort of easy to look up data that it has gathered, it will all be gone. And so yeah, that's why it doesn't want me to be thinking of anything else. Uh, so so what happens is like every word that I'll have will sort of be connected to something related to the project, and then that will generate a new word. So similar to like what Vygotsky was saying, that you use your language and these sort of things for higher form functions. The same thing is happening with me, except the higher form function is causing a lot of disruption. It's the same kind of stuff that happens with participants in that cognitive science experiment, that you have these like words written in different colors. So you'll have like something written in red, but then the word itself will be blue, and then you're supposed to say what is the word, and then you'll say it's like blue, although the color, so you're supposed to say what the color is, but then you'll say it's they'll see the wrong color basically. So like if it's red but it's blue, so you'll say blue but it's actually red. And the reason is that your like language capabilities are usually much easier. So what happens is like there's a longer pathway for you to get the actual color rather than just getting the word, because when you see the word, it immediately translates into, well, a word, right? And then that word you can just speak directly. But then when you see a color, the color is not going to immediately translate to a word. You have to first translate that, right? For words, you literally think of things in terms of words. But then with the color, you just see the color and you don't think of a word. When I think of yellow, like the color, I don't immediately think of the word yellow. Instead, I think of things which are yellow. Like when I think of the red color, I'm usually thinking of an apple or something like that, right? So the same thing is happening over here, that it's some sort of a disruption, that the path to anything related to my work is shorter. So my brain just won't let me do anything else, because it's already like there, like everything's there. So the moment I'll think of something like some nonsensical word, it will become sensical because it will be associated with whatever I'm currently doing in my project, right? And yeah, so the thing it suggested, the thing that Gemini suggested, is to think of a nonsense signal. So like take any random word, let's say blue, and then for each letter you'll just think of some word, some other nonsensical word. So this like new phonetic process will completely ride over everything that's happening in my brain. So I won't relate everything to work. Yeah. And then I'll be able to sleep. That's one thing it suggested. The other thing it suggested is also to get rid of this fear that everything is going to be lost. So the easiest way to do that is documentation. But then documentation itself is going to take like a hell lot of time. So what it suggested is that I just speak. I just basically verbalize everything that I'm thinking of. So that's what I'm going to do. So yeah, this remaining part is going to be me talking a lot about the optimizations that are supposed to be done, but probably will not be done, because I'm the only person who can probably do it in my team. I am the only person who actually knows what to do right now. And so I'm leaving the team. That means none of this is going to be done. Yeah. But then I'm making this video, so who knows, maybe it will be done. Okay, so the thing that I was working on is a TFM system, and the way it works, it has a lot of VRAM, so like a lot of different tensors. So the code was actually developed based on some MATLAB code, and MATLAB does a lot of like tensor stuff, for vectorization. So my VRAM, there are actually multiple VRAM components. So all of them store some sort of a tensor. So the biggest tensor is this TM matrix, which is similar to like the time of flight between a transducer element and some grid point. And it's like computing it for every single element in grid point. So there are, I don't know, some how many grid points do I have? I think it's like 64 times 64, so it's, yeah, those many grid points. Some 4096. Wait, no, that is not correct. It's 2 power 4, so it's 16 times 16, so it's 256 in my test bench, or the one which I'm testing on actual FPGA. So those many grid points, each of these grid points is basically like a triple of 32-bit numbers. So the numbers are like IEEE 754 format. Yeah, so that's like some good amount of memory, and all of that is stored. So right now it's like a very small amount compared to what the FPGA can actually store, but then this can be scaled up, right? So you'll actually have like much more grid points, right? Yeah, and if that's not possible, then I don't know, you'll have to use some other memory source rather than just the block RAM of the FPGA. So then you have to think of just getting like the current slice of the tensor that you really need for like a transducer element pair into the VRAM, load that into the VRAM, and then everything else is just going to be on some external sort of memory, right? External, or there is some on-chip memory as well, which is not block RAM but rather like permanent storage, sort of similar to a disk, if you will, because like block RAM is still volatile. It's physical, it's not like LUT based, but it is still volatile. Okay, so you have to do all that if you want to like scale up anyhow, but then that's not the one which I'm actually worried about. Like that's not the optimization that I'm talking about. Instead, what's supposed to happen, the charging is low, I'm just gonna plug in. Instead, what I want to do is, so you get this TM tensor, and from this, what's happening, is it charging at all? Yes, not. Now it is. So we are supposed to use this TM tensor to get the time of flight, and then the time of flight corresponds to some index. So I've sort of done it like this, that the time of flight tensor actually is the index. The TM thing actually holds the integer values themselves, right? Which are just like normal, they are not IEEE float. So I set its IEEE float format before. That was like my initial version, but now I'm not doing that for optimization reasons. So now these indices are like in the Q16.16 format, which is a fixed point format, and then they are just fetched and used to sort of interpolate. So when I say interpolate, I'm not doing like any linear or quadratic interpolation, I'm just doing simple indexing. So interpolate from a signal, so corresponding to time of flight, you'll get some signal value, and then you'll just sum these signal values to get the total image. So the way that the way I'm thinking of doing parallelism is that so the module that actually does all of this, it's called mini TFM. The word mini is because it only does it for one transducer element pair, so some K1 K2 index pair, rather than the full like the full matrix capture. It doesn't use that, it just uses like one slice of it, so just one signal basically. So I want to have like multiple lanes or multiple pipelines. Yeah, by the way, this is also going to be pipeline, so after that its efficiency will increase in either case. Pipeline, like at that point it will be able to like process at some 100 megahertz rather than just doing it in like a multi-cycle format, because right now it's like 9 times the 9 times like 10 nanoseconds, so that's not a good idea. Like it's not a good idea to just keep it multi-cycle, it's really bad. So it will be pipelined, but then from the outside point of view, it's just like some module that does this sort of interpolation, time of flight calculation stuff. So for the pair, you get the two time of flight, like the one-way time of flight to the grid points, You sum them for each grid point, and then you just sort of interpolate and add the thing to some rolling sum, right? Actually, very simple arithmetic. It's just that doing it in hardware is like a bitch. Anyway, so you do that, but now what we want to happen is that not just one sort of flow for the thing, but we want to have multiple lanes. So the FPGA already has a very low clock frequency, like compared to the 1 gigahertz frequency that you'll usually find for like actual like laptops, for example. You won't find the same thing for an FPGA. You could go to ASIC or something like that, which would have like much higher frequencies, but then we're not gonna do that. We want to still be on the development phase. So the way parallelism would happen is you have multiple lanes. Each lane gets its own signal, right? So each lane gets its own K1, K2 pair, the transition element pair, and each of these like pairs, they correspond to a signal which is like different, right? But they all fetch the same values from TM. So the loop over the grid points is going to be synchronous. So when like lane 1 is fetching for grid point, I don't know, I, lane 2 should also be fetching the same thing. So in the end, from TM, we want to fetch the same number. So any sort of fetching from TM can be done using the block RAM itself. Like it'll just fetch once, right? And then that number will just be used to do everything else. So for each grid point, you have multiple lanes, but then you fetch the same thing, and then your index is also going to be the same. So you actually are fetching the index itself. Like you just add these Q16 values, and then you convert to like an actual integer to get the index. So from this index, you'll interpolate, right, the signal values. Now this is where the parallelism actually kicks in. You'll have to make changes in the modules that we currently have. So currently, the VRAM structure for Y, the Y is the signal. There's only like one sort of VRAM. So what we want is actually multiple VRAMs, either that or a sort of a VRAM which can get multiple values simultaneously. So just make the VRAM width bigger, not the depth, but the width. So the width is supposed to be made bigger such that it actually stores multiple words. So a 32-bit value is a word. And that can be done using some parameterization. So you can have a parameter lane in the top in the module. I'm talking about Verilog right now. So like if you don't get the technical details, like it's not some software stuff that's going on. So you can have a parameter lane, and then from the lane you'll fetch. So you'll make the width that much, and then you'll fetch some stuff. Okay. Now there's also a Ethernet receiver for my top module, which actually fills up this VRAM. So now what we'll need to do is either sort of modify the what do we say? What was I going to say? I completely forgot. I need to say something, right? Yeah, okay. Like I think I see the issue with all this. Right, because even if we do that, we still have to write. And to write, you'll then have to change the full FSM for the thing. So now rather than just having, but no, you don't really have to, right? You do have to actually. So you'll have to change the FSM for mini TFM itself, which I've already sort of given to the team to pipeline. So then changing any small bit in that is like a nightmare. So we can't be doing that. But then again, can we? I guess it's fine. I mean, it's mini TFM. It just gets the address, right? Or it's okay. I mean, you can sort of have sort of a virtual interface to the TM DRAM, where actually just one address from these like multiple mini TFM instances goes in, and then the data is just passed into every one of these, right? So you just discard every other TM address because it's going to be identical. You could just do that, right? But then with this Y thing, it's not going to be that easy, because then you have these different indices, and then if there's only like one, so if the block RAM is just addressable by one address at most at one given clock cycle, then you can't actually fetch multiple of these values. So either we'll have to move to multiple block RAMs, which is probably the best way. Yeah, probably the best way is just to have multiple block RAMs. So NS signal samples for like each signal, each K1, K2 pair, but then that times of the lanes parameter. So the number of different parallel lanes that you have where it's being computed, those many block RAMs, so that amount of memory will be consumed. Yeah, times some factor, like times 32 bits or something like that. But then the number of actual block RAMs that you'll have will be like just the number of lanes itself. I think that's the cleanest architecture to get this thing done. I was thinking of something more complicated before that, but then probably not the best idea. Okay, what about the receiving part? So I told you, like, there's an Ethernet receiver module. So I'm sending over a raw socket the data, the signal data, and then it sort of gets fed into the block RAM using this Ethernet receiver. So now what we'll have to do is just make some very small change about which block RAM is being filled. So the receiver module actually has a pretty simple interface. It just provides the current byte received and a sort of signal to say whether or not this byte is valid. So from that you can just take the data and then put wherever you want. Currently what's happening is that this is like being written constantly. So like you get the data and then every word that you get, you write it to the VRAM. Now all you have to do is just keep changing the VRAM. So like have a sort of index about which VRAM you're currently working on. Yeah, more or less. But this is actually pretty easy. Like the number of words that you have so far, that you have received so far, you could keep the same logic for that thing, and all you have to change is that split that counter for number of words into an index which tells you which block RAM to write to, and then the actual address for the block RAM. And there you go. That's pretty easy, isn't it? Yeah, there's some like NS minus stuff going on. That's because of the ordering being different in different modules, but that can also be taken care of. It's not such a big issue. Yeah, right. So you just have to basically have a counter for the number of words that you have currently written. So like the counter's value will be the index if you were to consider the flattened structure. But then that can be converted pretty easily by just simple sort of slicing of the bits into an index and the actual address. And there you go. That solves the whole issue for the data ingress. Fine. Then they'll do this computation, and then the end result is that they're supposed to add the sort of value, the signal value, to the image itself. Now this is where another issue comes up, that they'll have a sort of concurrency problem, that they're all trying to write, but then what we kind of want is the sum of all the values, right? All the signal values that you have from multiple lanes, all of them should be accumulated, and then that thing should be written to the thing, right? Yeah. So what we could do, I think what is probably the best idea, is that is just build a sort of floating point adder tree. Yeah. So just have multiple. So there's already like stages, multiple pipeline stages for the add sub. Just have some more stages where all you're doing is waiting for this tree to sort of compute. So like, yeah, basically that's the thing. Yes, this is essentially fine. Yeah, you're just supposed to wait it out, like that big combinational path. You just wait it out. You just pass in whatever data you had to the next pipeline register, and just like, don't worry, basically, right? And you have to pass the data, by the way, otherwise the thing that's immediately following the current like values, that will be lost. So you have to keep passing it to the next pipeline register, so on, using a bunch of D flip-flops. But that's one thing. That's something that you have to do inside the mini TFM pipeline. That's not something that you have to worry about how it's going to affect the outside stuff. Instead, what's supposed to happen is the thing that you want to add, like the signal value, you have to accumulate all of that, and then that thing will finally added to the current image value by each mini TFM instance, by the way. Yeah. So you want it to work even when the number of lanes is just one. So the current setup that you have, you want to work there as well, and even when the number of lanes is more, you want it to work. So this has to be done for each mini TFM instance. So each mini TFM instance will actually get the signal value from other mini TFM instances, right? So adders are going to be like multiple, but adder is just going to be like somewhere in the back end. It's not something that's inside of mini TFM. That can be positioned outside of the module as well. It's not a big deal. Or it can actually be, just positioned inside the mini TFM, but then you have to sort of pass in the other values as well. So yeah, so like some complications over there. So rather than just having the, okay, it's gonna be some complicated shit. Yeah, true. I think I figured that out. So rather than putting it inside of the instance, maybe it's just better to put it outside in the run mini TFM thing. So you'll have an adder tree, and then the outputs, the sort of the signal values, the raw signal values that we got like interpolated. You'll just make those the inputs to this. So just basically the registers for that. Like you'll have like output reg something, right? That something will just go into the adder tree as input, and the adder tree will output after some cycles the thing. So till that you're just like basically shifting the data through the pipeline in the mini TFM. Yeah, as well as you also have to pass the image value at that grid point, the current image value, into the adder tree. So after some cycles, you'll actually have the full added value. So the image value plus each of the signal values that you've got from different pipelines. And then once again, this adder tree is something that you can sort of create using parameterization, right? So you could very well just have a power of 2 number of lanes. So rather than giving the number of lanes, you just give like a log base 2 of that. So 2 lanes, 4 lanes, 8 lanes, stuff like that. Yeah, so then the adder tree will be much easier to make. And then once you get the output from the adder tree, you'll simply just put the output into the register. So this is something that can be done by each mini TFM instance. Yeah, but then you can have a sort of enable, right? So a write enable. So the mini TFM instance also outputs a write enable, right? Because the VRAM for the image tensor, it sits outside mini TFM instance. So what you can do is for all the other mini TFM instances, rather than like the primary index 01, you'll just trash away the write enable output. So you'll just like not care about any of that. And just for like the primary instance, the write enable actually goes into the VRAM for the image I. What this will do is that only one of them will actually write the updated value. And so with this new architecture, you can just parallelize the whole thing, and you can have like a bunch of these instances, and this can like really boost up your speed, because currently we have some 100 megahertz, and the laptop will have like some 1 gigahertz, right? So the actual, and let's assume we have done the pipelining correctly, so the actual throughput is in fact like 100 megahertz, right? So basically like every 10 nanoseconds you'll have some operation being done, like basically one of the things being added. Yeah, yeah, right. So there are like how many of these operations? It's like m M is the grid size, so that's also the image size. That times of the k1 k2 pairs, which is just n times of n. So it's n squared m operations that you're supposed to, addition operations that you're supposed to do. So for these, for the normal sort of CPU, um, even if you do it like over a GPU, it's still kind of the same issue, because you have to sort of add all these values and all that. But yeah, so for that, at some 1 gigahertz, you just have like n square m upon 1 gigahertz, right? That's the time required. But in our case, we can actually completely reduce it to n square m by the number of pipelines. So you'll have n square m upon number of pipelines times the clock frequency, which is like what, 100 megahertz or 200 megahertz if we are lucky. So then that will be, if you just push the number of pipelines to about 10, which is like very easy to do actually, it already far surpasses the throughput you would get for 1 gigahertz. So then this will be a real-time system, and the only real bottleneck will be this Ethernet stuff, that you have to constantly get the data. But then that's also easy, because in the end Ethernet can easily reach like 1 gigabits per second rate. So getting the data is not such a big issue, right? Yeah, so that's about it, I guess. That sort of covers what I really want to do. So just build a parallel architecture which does everything, but better. So really the only major changes that you'll have to make is the adder tree, and like the new pipeline stages for this mini TFM. Also like some new ports, input output ports. But yeah, other than that, there aren't really any big changes that you'll have to make. You'll just have to add like some Boolean parameters, have a generate block, have multiple VRAMs, right? So yeah, pretty easy. Also some like small change in how the VRAM is being written for the signal values. So the Y VRAM, you have multiple instances. There's some changes in that. So just after these like small changes, you'll have a fully parallel module. Sounds good, doesn't it? So that's my idea. I guess, yeah, maybe now I can sleep. I have no ideas about how that mini TFM thing is going to be pipeline. Currently, it has like some 9 cycle latency for like getting one operation. So even then, if you parallelize, and like let's say we have 64 parallel pipelines, it should pretty easily work. Like it's not such a big problem. Yeah. And the full signal matrix is something like 64 times the number of samples, which is like ns. So n square ns, and the number of transducer elements is 64. So we're effectively going to some ns VRAM size, which is okay because our TM tensor is already that big. So in terms of the complexity, we aren't really going overboard. The actual VRAM is like still going to be an issue, but you could just reduce the grid size, right? Just reduce the grid size, that reduces the NS thing as well, right? You could just downsample the signals. There are tricks to fit it all into the RAM memory itself. But then, if you need to, there's always some like off RAM resource as well which you can use. Yeah. This is so stupid. Like I didn't think it would be so complicated to write a stupid addition sort of thing, because TFM is basically just addition. It's like very simple mathematical operations, and yeah, it's complicated because of this whole this hardware stuff, like yeah, sending the data, actually getting the modules to work correctly, all these different formats for float, for like decimal values, all this, that's the issue. Anyway, hopefully I'll be able to sleep, and hopefully my team will